Welcome everyone to this final intern talk by Benjamin Stahl. He was with us for the summer working on speech quality estimation. He's usually outside of here is a PhD student at my alma mater actually, the University of Music and Performing Arts in Graz in Austria at the Institute of Electronic Music. And he's going to talk about speech quality estimation today. And with that, Benjamin, take it away.
Good morning, welcome to my final talk on the topic Distilling Self-Supervised Learning-Based Speech Quality Assessment into Compact Models. As Hannes said, I was here from April to July. I just go right into the matter of interest. What is computational speech quality assessment and why do we need it? So the motivation is to use a computational model for speech quality assessment where evaluating the quality of speech recording in listening experiments is too costly, too time-consuming, or just impossible. So how is speech quality typically evaluated? In various applications, it's done like that. There's a speech recording, might be degraded speech by noise, or even generated speech. And then there are multiple raters, and each of them rates an opinion score, typically on a scale from 1 to 5. And then the scores of all raters are averaged, and this average score is called mean opinion score. And now we can do the same thing with a computational speech quality assessment model. That would give us the estimated mean opinion score. And as it's shown here, there is only one input. So that's the degraded speech. So that's called non-intrusive computational speech quality assessment, as there is no reference. Applications of this are for model selection or hyperparameter tuning in the development of speech processing systems, for determining the quality of data sets as a cost function, potentially, in an unsupervised setting, if it's a non-intrusive model in personalization of speech enhancement systems, and also to determine the quality of an actual product. So for my internship project, I collected multiple data sets. This is just to give an overview. These are the test data sets I used. So there is PSTN, which is public switched telephone network, then various other voice over IP data sets, some of them from the conferencing speech challenge, NISCA data sets. I also used text-to-speech labeled MOS data. So there's an English and a Chinese data set, and also French. This is from the Blizzard challenge, French text-to-speach and voice conversion. And then there are 3 internal data sets. These are from the submissions to the DNS challenge, Deep Noise Suppression challenge, to the packet loss concealment challenge, and to the signal improvement challenge. All of these challenges have been organized by Microsoft, by Teams. And additionally, there was also an extra internal data set that I use for evaluation. This data set has unprocessed and processed speech and is used for improvements of Microsoft products and services. At this point, I want to say thank you to Xavier from Teams for doing the evaluations on this data set. So I selected some state-of-the-art baseline models. First of all, there's DNSMOS. It's a widely used model. It's CNN trained from scratch on the DNS challenge submissions. And there are two models. There is a P808 and a P835 model. P808 only estimates MOS. P835 estimates MOS overall, SIG and back. SIG means preservation of the target signal, and back means disturbance by background sounds. Then there's the NISCA model. It's a CNN plus transformer architecture. It was trained on ratings of 5 different aspects. So as opposed to P835, it's not 3, but even 5 different aspects of subjective quality on the NISCA dataset. And this is English and German voice over IP speech data. Then there's a model that takes a little bit a different approach. It's called Torch Audio Squim. This is not trained on MOS data, but actually on outputs of full reference teacher metrics. So it's a RNN and 3 transformer prediction heads for PESC, SISDR, and STOI. All of these are full reference metrics. And this has been trained on the data from the DNS Challenge 1, enhanced by 3 different systems. To also include a MOS estimation system for text-to-speech, I included UT-MOS. This actually uses a self-supervised model as a feature extractor or front end. It's WAV2VEC2 and BLSTM MOS prediction head. And it has been trained on English and Chinese text-to-speech MOS data from the Voice MOS Challenge. And finally, a very recent approach is XLSR SQA. So the authors of this work did a grid search on different intermediate outputs of WAV2VEC XLSR. XLSR is just a very big WAV2VEC2 model trained on huge amounts of speech data. And then they use a transformer MOS prediction head to predict MOS. This has been trained on the conferencing speech data and was actually the winner of the conferencing speech challenge. So I did an evaluation on the data sets I just showed. I forgot to mention I also have this metric here. This is to say what's the quality of the data set. As you can see, it's 1 minus the average of the, actually that's a sample variance. So it's the variance of the opinion score divided by the number of raters. So that would be an upper bound of the correlation coefficient. And what do we see in these results? So we see that text-to-speech data is generally hard to predict, except for UT-MOS, which was actually trained on text-to-speech data. What we also can see is that DNSMOS and NISCA don't perform really well on the signal improvement task. And as opposed to that, XLSR shows quite good generalization to these tasks, even though it wasn't trained on any of the challenge submissions. So what can we conclude? The XLSR embeddings show a good generalization for the speech quality assessment task. And we did further experiments with these embeddings, looking at embedding distances, and also we trained small MLPs on embeddings to confirm these findings. just to show one result, this one is we use the VCTK as a clean reference speech data set, and then we computed the average L2 or Euclidean distance between each sample in that data set and the signal under test. And this should be inversely correlated to MOS if the embedding is good for speech quality assessment. And as we can see, we compared 3 different embeddings: XLSR, NOMAD, which was an embedding that was specifically trained for that task, and CLAP. And also, even though XLSR wasn't specifically trained for that task, it shows, actually quite good correlation with MOS here. And that's why we decided to use XLSR and transformer as a starting point. As a quick explanation, what's behind XLSR? This was trained like all the other VAF2VEC2 models, contrastive masked region prediction pre-training, and it has seen 436,000 hours of unlabeled speech. And the idea is that audio degradation as a feature of speech recordings can be predicted from context and is therefore surfaced by these embeddings. So now that I actually wanted to train something, I just show what data was that I used for that. There were dedicated training and validation sets for some of the test sets I used. PSTN, Tencent, Niska, and VoiceMOS challenges had this. And then I also used the other, as I showed earlier, I used DNS3, PLC 2024, and SIG Challenge 2024 for testing, and used the earlier challenge submissions for training and validation. I also did a train and validation split to make sure validation data doesn't contain any of the same input signals and also not any of the same submission models. This shows the percentage of the training data, and as can be seen, this is quite an unbalanced percentage. For example, PSDN is more than half of the data here. That's why for training I used a sampling scheme where I changed the distribution a little bit. So what were the experiments I did? The correlation of XLSR of the original model with subjective ratings were already quite high, and it was actually not that easy to improve on that. What I tried was, one thing was a full band extension, a direct CNN-based connection around the embeddings, and also extending the XLSR embeddings by other embeddings. Then replace the default center cropping that was used in the original XLSR SQA paper by random cropping in training, and add dataset bias awareness. And only 2 of them actually led to small improvements. So here are the results. As can be seen, here is the weighted mean is 0.78 for the Pearson correlation coefficient for the original model, and with including all the data and all the internal data, also I could bring it up to 0.81 with a model that had the same architecture but used this bias-aware training and random cropping. So correlation to subjective ratings are now already high, but the model is quite large. It's including the embedding model, it's 1.8 gigabytes. And if I remind you of the applications that I earlier talked about, there's model selection, determine dataset quality, but the other ones, cost function, if I want to use this in a personalization setting on device for a user, or determine quality in production, it's not possible because a product with a 1.8 gigabyte speech quality assessment, it won't ship with a 1.8 gigabyte speech quality assessment model. That's why that was the motivation to reduce the model size. And the approach I chose for that was to distill into more compact models. So XLSR, the self-supervised learning model, has more than 400,000 hours of speech trained into it. And it certainly surfaces more features than just the quality of speech, which are unnecessary for the tasks. And therefore, I came up with this scheme here, where I used the SSL-based speech quality assessment model as a teacher. And I'm trying to distill only the important parts of these features into a more compact model. And my apparatus here is a training pipeline with an unlabeled data set. So one could use the estimated MOS by the teacher model as pseudo-labels to train a student model. I developed I implemented an on-the-fly data generator for that. This has speech, noise, room impulse responses from the DNS4 training data, which is approximately 2,500 hours of clean speech. Then text-to-speech models. I used 17 different models. Parts of them were multi-speaker models in 5 different languages. Speech enhancement on the noisy speech, generated noisy speech data with 4 different approaches. Vocoders and codecs to span quite a large bandwidth in what can be done in terms of speech processing. And just to show here what are typical examples here, and and the ratings of the teacher model. So here we have a model, a sample that is rated quite high by the teacher model.
Los cabecillas de la banda huyeron a caballo.
So SNR 22 dB and also a state-of-the-art speech enhancement model. Then Text-to-Speech.
Ich bin der Schild, der die Reiche der Menschen schützt.
I now show something from the mid-range. So this is something where you hear oversuppression.
Jahrhunderts. Jede mit 4 Jahren erkrankte Itzhak Perlman an Poliomyelitis. Er konnte
Und die Rheintalbahn seitdem kreuzungsfrei überbrückt wird.
Yeah, also some
Ziel
residual
der
noise
Streckenverlegung
and also bad SNR.
LZB-Schleifen gewährleistet. Eine weitere LZB-Schleife dient der sicheren Abstandshaltung.
Okay, so now we have the teacher model, we have the unlabeled data set, we need a student model architecture. I decided to do something that's similar to the NISCA convolutional neural network and transformer model. The input is STFT domain compressed, then compression, using a complex compressed representation, and then a CNN with these complex compressed features as an input, a transformer pooling attention that then regresses onto the estimated MOS. And I came up with 10 different versions of these to span 2 orders of magnitudes in model size and computational cost. So here, by varying the CNN, the number of convolutional channels, the number of the dimension in the transformer, the number of attention heads, the number of layers in the transformer, and that then gives you these multiplier accumulates the computational cost and the parameters. So this goes between, what is it, 1 gigameg to, what is it, 20 gigamegs or something. And this goes between 100,000 parameters to 25 million parameters. And as a distillation strategy, as I just mentioned, I used the SSL-based model as a teacher to obtain pseudo-labels. And then I experiment with different percentages of mixed-in labeled data, 0, 10, 20, 40, 80, and 100% labeled data. 100% is the labeled only baseline that doesn't do any distillation. And to also have an alternative for model size reduction, I also did pruning. So this starts from the full model, and I tried 2 different strategies for pruning. One is magnitude-based pruning. For that, I used the absolute value of matrix elements or the L1 norm for convolutional kernels. And another method is importance-based pruning. So there's an approach where there's a so-called importance of a weight, which is the loss function minus, or the Euclidean distance, the squared distance between the loss function with the model with a certain weight and the model with the weight set to 0. And this importance can be approximated by its first order Taylor expansion, which is just the gradient multiplied by the weight value squared. So the strategy for pruning was use a leaky integrator for averaging the importances across batches. Then every 30 batches, I remove 0.5% of the weights and fine-tune along with the pruning process. And the same fine-tuning and removal schedule was also used for the magnitude-based pruning. I also experimented with mixing in unlabeled data and pseudo-labels from the unpruned model with pruning. So these are the results from the distillation. I only show, in this slide, I only show 2 distilled models. One distilled model with 4 million parameters. The original XLSR model has 450 million parameters, so this is 2 orders of magnitudes smaller. And if we look at the weighted mean test PCC, Pearson correlation coefficient, we can see the original one has 0.81. Then for the baseline that doesn't use distillation gets 0.72, and we can close actually a little bit more than half of the gap between the baseline and the SSL-based model using this distillation approach. It gets a little clearer on the next slide. So here, this shows it for all the 10 model variants. And as can be seen, the labeled only models, they overfit if the model size becomes too large, has an optimum here. And the distilled model keeps getting higher performance with a larger model size. This one is the original model, so yeah, here this closing a little bit more than half of the gap becomes clear. Here this one is DNS MOS as a reference. Yeah, just said it. And then for the pruning I also have results. For time reasons, these are only preliminary results on the validation set. But it can be seen that, yeah, the curve for the distillation looks quite the same. There's a saturation at large models. And magnitude-based pruning doesn't really work. But this is kind of obvious because the self-supervised model isn't task-specific, so you just prune away without looking what is important for the task. And importance pruning actually can bridge the gap at larger model sizes. As a caveat, these model sizes here are given without the indices for the sparse matrices. One would have to multiply the model size approximately by 2 if we used 32-bit values and 2 16-bit integer for each matrix entry. And also what showed was that for the pruning there was no difference in adding unlabeled data and pseudo labels, so that didn't matter if we pruned only on labeled data or on unlabeled data as well. I have some other interesting findings on the test results. So I already mentioned earlier that text-to-speech voice conversion MOS is harder to predict than voice over IP or speech enhancement signal improvement MOS. And adding text-to-speech data from the training split of a certain test can improve the of a certain test split test set can improve the performance on that test set, but doesn't improve performance on the unseen text-to-speech data sets. So what we can see here, even though we added the English and Chinese training data, the French text-to-speech data wasn't better than without any text-to-speech data at all. And also, what's interesting is that the distilled model distillation didn't really help with that. So it seems to amplify the errors that the teacher model makes, even though there was French speech in the distillation data. So final conclusions. I compiled a MOS dataset with more than 180,000 labeled samples from public and internal data. Then compared state-of-the-art computational speech quality assessment models, verified the adequacy of XLSR features, developed distillation and pruning schemes for reducing the model sizes, and also exported ONNX models to ease further usage. So thank you for attending, and I'm looking forward to your questions.
Yeah, very nice talk. Maybe more feedback than question. I think we had this. I think it was in Haibin's talk where we also talked about how difficult or different is the prediction of generated speech, because your models perform not that great on that one. And I think one reason might be that also different test like evaluation runs, you don't often even know what raters are rating in speech generation. So there are two main objectives. One is the acoustic quality, and the other one is kind of naturalness, which includes like speech prosody and how actually natural the speech itself is. And maybe even though you distilled this on a large data, but I think you didn't distill the knowledge on actually generated speech.
I have
right?
generated
You
speech,
have?
but it didn't
Okay.
help. It seemed even
Okay.
to amplify the errors
Yeah.
that the teacher model did with that kind of with French. I had French speech in the distillation data, in the
Yeah.
unlabeled data, and the teacher model isn't that great in that domain. But the student model was even worse.
Yeah. Yeah, but that's an interesting fact. Yeah.
Maybe can I ask, like, just as a follow-up to what Sebastian said? I actually thought the slide with where you show, like, I don't know if it was a random batch or if you handpicked some samples, but the slide where you showed I think it would be interesting to actually have like a couple of judges judge those samples and see if you get that same ranking, because these are ground truth MOS scores from very different. These are the teacher MOS labels, but they would correspond to ground truth MOS scores from different test sets with different types of tasks or degradations. And while raters might agree on certain set of MOS ratings within one task, like generated speech or noise suppression, ranking them like this is actually quite hard because it's an apples to pears comparison, right? You have a very nice sounding text to speech with some codec artifact compared to natural speech with distortion and background noise, and it's not straightforward to say. So one way maybe around that, or maybe one extension of the model could be just like DNS MOS, like 835 does. You predict either multiple MOS scores that come from different sets, or predict the degradation along with, or the type of speech signal along with the MOS score. So if the model also is forced to distinguish between synthesized and real speech and estimate SNR and stuff like that, it might help disentangle some of that. Yeah. If you want to. Oh, you have a mic. That's right.
So I don't need to wait for the answer to. Okay. Thank you for a very nice talk. My question is, I'm not sure that I'm getting everything, but from the XLS, your baseline XLSR, I think it was called, I got that had already a very high correlation with user scores. You're trying to improve on that, but I expect the users to also have some sort of disagreement amongst themselves. So my question is, okay, there is probably some inter-rater disagreement. The XLSR is already has a very good correlation with the scores. So until what point does it make sense to try to improve on this, if there is some disagreement between people already?
So,
like, aren't we, like, maybe you're already at maybe the baseline is already like maxing.
that's why I computed these
Perfect.
values actually that I show in the first row here. This gives me some certainty of the MOS. There is some disagreement, but still, it's always the case that individual ratings have higher variance than a MOS prediction model has, and that's how it should be, because it's mean opinion score that is predicted, And the quality of the data depends both on the variance of the raters and the number of the raters, and that's what I tried to include here. There are some data sets where it's already quite close, but on most of them, I think there's still some room for improvement, even with some variance across opinion scores.
So for this first data set, the PSTN, for example, the inter-rater agreement score sort of is 0.82. And then the top row?
That's not inter-rater agreement as far as that's why I divided by the number of raters to take into account how the sample mean variance is reduced by having more raters.
Okay,
It's a proxy.
It's also
It's
a
a proxy,
quality
yeah,
metric for the scores.
Yeah.
In that data set, okay, yeah. And then we see that also the models have lower.
Yeah.
Okay. Yeah, that makes sense.
It explains actually the general difference in performance across data sets is to a large amount explained by the data set quality.
Yeah.
Maybe there are some ways to visualize this, to remove this part, to visualize what actually is epistemic uncertainty here. Yeah.
Thank you very much.
Maybe it's hard to grasp, but maybe one little graph to compute is can you compute the correlation of this reliability metric and the data set wise performance?
I could do that.
It's probably pretty good, well correlated.
Yeah.
Right. That would be an interesting metric.
Except for TPS.
Yeah.
Hello, hi. Yeah, thanks for a great talk. So I'm wondering whether the first row is about the variance for the same utterance or like for the entire data set?
It's computed for each. I compute the sample mean variance, which is variance of opinion scores divided by number of raters, and then I took the average over the full data set.
Over the full data set, okay.
Yeah.
So I'm wondering whether the model can do one simple thing, is just predict like which data set or which like model generated the speech, and then just assign the same score for the utterance, and that would be a. It's so just saying, is it the model just doing I think see a speech and then predict which data set it is in, and then assign the score?
You mean the model should predict the uncertainty?
No, I mean, so maybe the model can just do a thing that like classify which data set the speech comes from. And
I think Hannes mentioned it.
Oh. You get one prediction per file, not per data set.
No, but I think he's saying that the model somehow figured out that, oh, this was a good quality data set, and it just gives high prediction for that, whatever. If it figures out this is from this data set, there's a high prediction.
But good quality doesn't mean high MOS. Good quality in that context means high correlation of human labels or high certainty in the MOS. And we can quantify that certainty if we have the number of raters and the variance of the opinion score.
Oh, okay. So say that the Tencent dataset have like very high like agreement among the raters, but the score can vary like still largely within the dataset. Yeah. Is it? Oh, okay.
In fact, ideally it varies within the data set because otherwise there's nothing to predict.
Oh, I saw that there's an error in that equation. Yeah, the whole thing should be that the expected value should be divided by the total variance of the data set. So this expectation here should be divided by the variance of the data set.
Okay, yeah, thanks.
Okay, maybe. Yeah. One general question now that you've gone through all this work, and if you had to now pick a model yourself to use, which one would you? Because you have a whole bunch to choose from now, right? Which one would you think, and for what reason?
If I have enough computational resources in memory, I probably just use the XLSR-based model that has seen most of the data, which is the one that yields the highest weighted mean PCC here. If, let's say, I do some speech enhancement training and do validation every hour or so, and then of course it wouldn't matter how long that takes, and there I think a smaller model could be better. And also, if I would want to use this in some product that I would like to ship, model size is important.
All right. I don't see any questions on the chat. I don't see any raised hands. So I think let's thank Benjamin again for a great talk and for joining us this summer.